Welcome back. This is lesson 8, Openings and Nozzles. I am Reza Talukdar, and today we do something you might not expect from a pressure vessel course. We are going to cut a hole in the vessel we spent 7 lessons carefully designing. Every vessel has nozzles, feed lines, product lines, manways, instruments. Every one of those requires cutting a hole in the shell, and every hole has to be dealt with because pressure doesn't care that you needed a nozzle there. It's still pushing on the wall, and the metal you removed has to be accounted for. That's UG-37. That's lesson 8. Let's go. Before we open the code, let me tell you about a problem that framing carpenters solve every single day. This is a stud wall, regular wood frame construction. It starts every 16 inches. Top plate above them, bottom plate below. The studs carry the load from the roof down to the foundation. Now, suppose you want to put a window there. You have to cut out 3 or 4 studs to make room for the opening. But look what happens. The load that used to run through those studs has nowhere to go. The top plate sags into the opening. Cracks appear. Eventually, the roof itself deflects. So, what does the carpenter do? Install a header, a big horizontal beam right above the window opening, supported by jack studs on either side. That header now carries the load the missing studs used to carry. The load detours safely around the opening. The wall is sound. This is exactly the pressure vessel engineer's problem. Cut a hole in the shell, and something has to carry the load the missing material would have carried. In houses, we call it a header. In vessels, we call it reinforcement. Same idea, same physics, same math. That's the entire discipline of UG-37 in one sentence. Before we get into the mechanics, let's zoom out. Why do we cut holes in vessels at all? Turns out for a lot of reasons, grouped into 4 families. First, process connections. Feed inlet where the process fluid enters. Product outlet where it leaves. Recycle or reflux lines returning downstream streams. Vent and drain lines for startup and shutdown. These are the reason the vessel exists at all. Second, safety. Pressure safety valve connections. Rupture disc, emergency vents for runway pressure, atmospheric breather vents. These nozzles exist to keep the vessel from becoming a hazard when something goes wrong. Third, instrumentation. Pressure taps for gauges and transmitters. Thermowells for RTDs and thermocouples. Level connections for side glasses and level transmitters. Sample ports for lab or online analyzer. These are how we know what's happening inside the vessel. And fourth, maintenance and access. The manway, typically 18 to 24 inches for human entry during inspection. the handhole or clean out for tools, inspection ports for internal visual exam, chemical wash connections for cleaning between campaigns. Cutting holes is unavoidable. The code doesn't try to stop us, it tells us how to do it safely. That's UG-37, and it's what the rest of this lesson is about. So, let's ask a simple question. If we don't reinforce a hole, what actually happens? Start with a solid shell wall, no opening. Pressure inside pushes outward, creating tension in the wall. See these green lines? They are stress flow lines. Imagine the pressure load traveling through the wall from left to right. When the wall is uniform, the stress spreads out evenly. Every part of the wall carries its share. This is what internal pressure looks like in a healthy vessel. Now cut a hole in the middle. What happens to those stress lines? They can't go through the hole anymore. So they detour. They crowd around the edges of the hole to get past. Look at the pattern. The lines that used to pass through the middle are now squeezing tightly along the sides of the opening. And where lines crowd, stress crowds. The peak stress right at the hole edge can reach 3 times the nominal wall stress. 3 times. Those red dots on either side are the hot spots. And here is what happens if we do nothing about that. Under sustained pressure, or worse, under cyclic pressure, startup, shutdown, pressure swings during operation, those hot spots become crack initiation sites. Fatty cracks start right where the stress is highest, and they grow outward from the whole edge, following the stress concentration. This isn't hypothetical. This is exactly why we have UG-37 in the first place. Load doesn't disappear when you cut a hole. It detours. Where it detours, it crowds. And if we do nothing about it, cracks start. That's the motivation for everything that follows in this lesson. Here is our roadmap. 6 stops. 1. The area replacement idea. UG-37 in one cartoon. The whole lesson in principle. 2. 3 reinforcement types: integral, welded pad, and self reinforced forging. What each one looks like at the shop. 3. Limits of reinforcement. UG-40 tells us what metal counts and what doesn't. 4. The sources of replacement metal, and then the UG-37 equation. 4 physical sources. Then the formula. 5. V102 worked example. Adding a 6-inch feed nozzle to our tall column. And 6. The pad or integral decision. Cost, service, inspection. How designers actually pick. Let's start. Here is the entire lesson in one cartoon. 3 panels. Solid shell wall. Look at that red rectangle. That's a strip of material with area equal to hole diameter times required thickness. That's the metal that's about to be removed. Right now, it's still there, carrying its share of the pressure load. It's carrying an amount proportional to its cross sectional area, which is d times T sub r. Now cut the hole. That strip is gone. The metal that was carrying that load is not there anymore. And here is the thing, the load didn't go anywhere. The pressure is still pushing on the wall. So something has to pick up what that missing strip was doing. This is UG-37. We add back the area we removed in the form of extra metal around the hole, extra shell thickness, that's A1, extra nozzle wall thickness, that's A2, and often a reinforcement pad welded around the nozzle, that's A5. Add them all up. That sum has to be at least as big as what we removed. A1 plus A2 plus A5 greater than or equal to D times T sub R. Simple. Everything else in lesson 8 is just accounting. Where the areas come from, how they are counted. UG-37 itself is one idea. What you removed at the hole, replace at the hole. There are three main ways to add that replacement metal. All three satisfy UG-37 equally. The code doesn't prefer one over the others. The choice is about cost, service, and fabrication convenience. Integral reinforcement. Extra shell thickness around the opening. Machined or blended into place. No separate parts. The shell itself is locally thicker where the nozzle sits. Use this for small nozzles or when the shell is already thick from pressure design. Sometimes it's already thick enough that A1 alone handles the whole reinforcement job. Reinforcement pad. A separate ring of steel welded around the nozzle neck on the outside of the shell. See those weld beads? Fillet welds all the way around, pad to shell and nozzle to pad. This is the most common choice in most fabrication shops. Flexible, well understood, easy to inspect. If you underestimated the reinforcement requirement early in design, you can upsize the pad late without redesigning the vessel. And self-reinforced, also called forged reinforcement. A single piece forging with a thick neck built in, butt welded to the shell. See the difference in the weld pattern. Just one clean butt weld each side instead of fillet welds. No pad, no crevice under a pad where corrosion could hide. This is preferred for cyclic service, corrosive fluids, or high temperature applications where you can't afford weld crevices. The choice is about cost and service, not about strength. All three satisfy UG-37 peak based on the specific application. Most vessels in most industries use the middle option, welded pads, because it's the most economical for the majority of situations. But you will see all three at the shop. Now, here is a concept that trips up almost every junior engineer the first time they see it. If we can add reinforcement, why not just add it wherever? Why can't I count metal from 3 feet away? Answer: because that metal is invisible to the stress concentration. See this shaded box around the nozzle. That's the reinforcement zone per UG-40. It's the region where reinforcement actually helps. The code defines its limits mathematically, horizontally, parallel to the shell. The zone extends outward by the larger of the hole diameter d, or the sum of nozzle radius plus nozzle wall thickness plus shell thickness, whichever is bigger. Vertically, outward from the shell surface, the zone extends by the smaller of 2.5 times the shell thickness, or 2.5 times the nozzle thickness plus pad thickness, whichever is smaller. Here is the reason, and this is the sentence I want you to remember. Metal far away doesn't feel the stress concentration. Load sharing is local. The stress hotspot around the hole is a local phenomenon. It stretches only a few inches into the shell before the stress smooths out to normal levels. Reinforcement outside that zone is useless, not harmful, just wasted. UG-40 defines the zone where reinforcement actually helps. Any metal you add outside it is invisible to the code. Before we look at the UG-37 equation, let's answer a simple question in plain English. Where can the replacement metal actually come from? What are the physical sources? Turns out, four places. That's it. First, the shell itself. If we specified a shell thicker than what pressure requires, that excess thickness is metal we can count toward reinforcement. See those orange bands in the sketch? That's shell metal beyond what UG-27 required for pressure. If we are near a hole and that excess metal is within the UG-40 zone, it counts. We call this area A1. Second, the nozzle wall. Similarly, if we picked a nozzle wall thicker than UG-27 requires for the nozzle's own pressure calculation, that excess counts too. And this goes both ways. The extra metal projecting outward above the shell surface counts as A2. If the nozzle projects inside the vessel, that inward metal counts as A3, though most nozzles don't have inward projection. Third, the pad. If A1 and A2 aren't enough on their own, we add a separate plate around the nozzle. This is the main way to add area when the shell and nozzle come up short. It's the A5 you will see in most calculations. And fourth, the welds themselves. The fillet welds joining nozzle, pad, and shell have their own cross sectional area. Small, typically a fraction of a square inch, but real. And when your margin is tight, you will count them. This is A4. Four sources. That's it. Once you see them, the UG-37 equation on the next slide isn't a wall of algebra. It's just levels for what you already understand. Now the equation. And now you already know what it's saying. Required area equals D times T sub R times F plus 2 times T sub N times T sub R times F times in parentheses 1 minus FR1. Let's parse it. The first term D times T sub R times F. That's the rectangle of shell metal we removed. Hole diameter times shell required thickness. Nothing exotic. F is the correction factor equals to 1 for standard nozzles. You can ignore it in most cases. The second term with the 2 times T sub n and the 1 minus FR1 accounts for a subtlety. If the nozzle material is weaker than the shell material, we need more required area to compensate. If they are the same material, FR1 is 1, and that second term vanishes entirely. In our example today, same material, so we can drop it. Now the available areas, and every symbol here maps directly back to the sources we just looked at. A1 is the shell axis. A2 is the nozzle wall outward. A3 is the nozzle wall inward when it exists. A4 is the welds. A5 is the pad. Look at the row levels. That's exactly what we said. The code just puts levels on the physical sources you already understand. And here is the rule. A1 plus A2 plus A3 plus A4 plus A5 greater than or equal to A required. Total available area has to be at least the required area. Simple accounting. If you can make that inequality true, your nozzle is adequately reinforced per UG-37. If you can't, you need more metal somewhere. Now, let's put a face on the math. Here is what a real nozzle detail looks like on a fabrication drawing. You can see the shell wall along the bottom with its thickness T called out. Above the shell, a reinforcement pad. That separate plate thickness T sub E. The nozzle neck rising vertically. Its wall thickness is T sub N. The finished opening diameter is D, and the pad outside diameter is D sub P. Every one of those dimensions has a name in UG-37. Every one of them shows up in a term of the area calculation. If you can read this drawing, you can trace every UG-37 term back to a physical dimension. Shell wall, nozzle wall, pad, welds. And notice the welds. Two fillet welds at the pad to shell junction. Two fillet welds at the nozzle to pad junction. And a full penetration groove weld between the nozzle and the shell itself, deep inside. That's typical for a pressure vessel nozzle in most services. You want a full penetration weld through the shell for structural integrity, plus the pad and fillet welds for the reinforcement path. Fluency in nozzle details equals fluency in UG-37 term by term inspection. When you see a drawing like this in your career, whether reviewing a vendor package or checking a fabricator's shop drawing, you will be able to walk through it and confirm every area contribution. Now, here is a rule that every new engineer miss more than any other in this section. UG-45, minimum nozzle neck thickness. Here is the setup. You have done the UG-37 area calculation. You know what nozzle wall thickness you need for the reinforcement math to work. But there is a second check. UG-45 says the nozzle neck also has to be thick enough for a minimum standard, independent of the pressure calculation. Option A is the pressure calculation. Nozzle wall required equals P times nozzle radius divided by allowable stress minus 0.6 P. This is UG-27 applied to the nozzle as its own little pipe. It gives you a thin answer because nozzle radii are small, usually just a few hundredths of an inch. Option B is the shell thickness required for pressure, not the nozzle's pressure, the shell's pressure, with a cap from a table in UG-45. This usually gives you a thicker answer than option A. UG-45 rule. Nozzle neck thickness equals the larger of option A or option B, whichever is thicker wins. In practice, option B usually governs because option A alone would give you a nozzle wall so thin that any real world load beyond pure internal pressure like external forces from piping, thermal expansion, weight of the valve or instrument on top, wind load, seismic would deform the neck or fail the weld. So UG-45 protects you. It's the rule that turns I need a 1/8 inch nozzle wall into you need a schedule for the pipe at least. Don't skip it. And in the practical world, this is why every commercial vessel software you will ever use runs the UG-45 check automatically. Because if you leave it out, you are building an under-designed nozzle. So, here are the four sentences I want you to walk out of lesson 8 with. The hole doesn't fail. The path around the hole fails. UG-37 says replace at the hole what you removed at the hole. Not near the hole, not somewhere handy on the vessel, at the hole, in the zone where the load has to detour. That's the entire discipline of UG-37 in one philosophy statement. Time for our worked example. And we are going back to a vessel you already know. Meet V102 again, our tall process column, 72-inch diameter, 45 feet tall. Design pressure 305 psi at 730 degrees Fahrenheit. Full radiography, weld joint efficiency of 1. Corrosion allowance 1/8 inch. Same vessel we designed the shell for back in lesson 3, sized the head for in lesson 5, and picked the weld inspection for in lesson 6. Now we are adding a real detail, a 6-inch feed nozzle on the shell, 6-inch nominal pipe size, schedule AD, material SA106 grade B pipe, standard for process nozzle at this temperature, nominal wall thickness 0.432 inches, full penetration weld to the shell plus a reinforcement pad. The question is a pad required? And if so, how big? We are about to cut a 6-inch hole in a 13/16 inch wall. Let's find out what UG-37 says. Before we start the numbers, the standard disclaimer. This is an illustrative educational example. Actual nozzle reinforcement calculations must use the applicable code equations, dimensions, and material properties for the specific design. The numbers I am about to show you illustrate the method. They are not design ready. Don't paste them into a real vessel calculation. Okay, here are the numbers. Shell thickness in the corrugated condition 0.6875 inches. That's the 13/16 inch shell we specified in lesson 3 minus the 1/8 inch corrosion allowance. Shell required thickness per UG-27 0.605 inches. Opening diameter 6 inches. Nozzle wall in the corrugated condition 0.3 inches. Nozzle required thickness per UG-27 0.051 inches. Essentially trivial because the nozzle radius is small. F equals 1 and FR1 equals 1 because we are using the same material family for both shell and nozzle. Compute the required area. A required equals D times T sub R times F. That's 6 times 0.605 times 1, which gives us 3.63 square inches. So we need to make up 3.63 square inches of metal around the hole. Now let's see what we have got. Attempt 1. Let's see if the shell axis and the nozzle wall axis are enough on their own. A1, the shell axis, equals D times in parenthesis T minus T sub R 6 times in parenthesis 0.6875 minus 0.605. That works out to zero point 0.5 square inches. A2, the nozzle wall outward, equals 2 times in parenthesis T sub n minus T sub Rn times the smaller of 5t or 5t sub n. 2 times 0.249 times 1.5, 0.75 square inches. So total available without a pad A1 plus A2 equals 1.25 square inches. 1.25 square inches. We need 3.63, shortfall of 2.39 square inches. Not even close. Nowhere near enough. So we need a pad. Attempt 2. Add a reinforcement pad. Try a 12-inch outside diameter pad, 1/2 inch thick. A5, the pad, equals T sub E times in parenthesis D sub P minus D minus 2T sub N, 0.5 times in parenthesis 12 minus 6 minus 0.6. That's 0.5 times 5.4, which gives 2.7 square inches. Total available with the pad 1.25 plus 2.7 equals 3.95 square inches. And that's greater than the 3.63 we need. Adequate. Design passes. Verdict: 6-inch NPS Schedule 80 nozzle plus a 12-inch OD by 1/2 inch thick reinforcement pad welded per UW16. And we still need to run the UG-45 check to confirm the 0.432-inch nozzle wall meets minimum. It does comfortably. So, design complete. Now, let's zoom out. We just used a pad for V102, but we had another option: self-reinforced or integral. When does each choice make sense? Reinforcement pad. Pros: it's cheap to fabricate, easy to modify late in design if requirements change. Fits standard nozzles. You don't need to specify a special forging. It's what most shops do most often. Cons: there is an extra weld to inspect, and there is a crevice trap under the pad, between the pad and the shell, where corrosion or fouling can hide. For most non critical applications, none of that matters. Pad is the default. Integral or self reinforced. Pros: no crevice, no pad weld. Better for cyclic loads because the stress path is smoother. No sharp weld toes at the pad edge. Cleaner NDE. Higher inspection confidence. Cons: more expensive forging. Longer lead time. You have to specify the forging early and order it before fabrication starts. And it requires early sizing. You can't easily bump up the reinforcement if the requirement grows late in design. Finally, company standards and client specs vary widely. Some clients require pads on everything for consistency. Some clients require integral on all high cycle service. Use these guidelines as starting points, not universal rules. Check what your organization does and what your client specifies. Real vessels usually have multiple nozzles, and sometimes those nozzles are close to each other, close enough that their reinforcement zones overlap. When that happens, UG-42 applies. Far apart, each nozzle has its own reinforcement zone, and the zones don't touch. Simple case: design each nozzle independently, same as if the other were not even there. Rule of thumb: if the center to center distance is at least twice the average of two hole diameters, they are independent. But if the nozzles are close enough that their reinforcement zones overlap, look at the dark red region. Then that shared metal can only count for one nozzle, not both. That's UG-42. The math for this case is more complex. You do a combined calculation treating both nozzles as one system. Vessel design software handles this automatically, but you need to recognize when it applies. Shared metal in an overlap zone counts for one nozzle only, not both. That's UG-42. Design tip: if your layout has nozzles closer than about two hole diameters apart, either move them apart or expect a combined reinforcement calculation. Time to update the engineering notebook. Three vessels, three different nozzle stories. V101, our small air receiver. Nozzles mostly integral. Why? Because the shell is only 1/4 inch, governed by handling minimum, not pressure. So it's actually thicker than pressure required. And small nozzles pass the UG-37 check just from the shell access. No pads needed. V102, our tall column, the vessel we just designed a nozzle for. 6-inch feed nozzle needs a 12-inch by 1/2-inch reinforcement pad. Larger nozzles will also need pads, highlighted in orange because that's the addition from lesson 8. V103, our vacuum tower. Large nozzles, the vapor outlet, the feed nozzle, the manway all need reinforcement. And because V103 sees external pressure, its nozzles also need to be checked per UG-38 for buckling. That's on the next slide. Three vessels, three different nozzle stories. Same UG-37 discipline for all of them. Quick callback to lesson 7. V103, our vacuum tower, sees external pressure on the shell. And guess what? The nozzles on that vessel see external pressure too. Look at this. The vessel is under vacuum. Atmospheric pressure at 14.7 psi pushes in on the shell. That's the UG-28 problem we solved in lesson 7. But atmosphere also pushes on the outside of every nozzle neck. Nozzle necks are cylinders. Cylinders under external pressure can buckle. So UG-38 says check them too. 4 things to know. 1. Same UG-28 procedure applies, just using the nozzle diameter and length instead of the shells. 2. In practice, most nozzles pass the UG-38 check easily. They are short, they are thick, they have low L over D and low D over T ratios. 3. Watch out for exceptions. Long vent stacks, blow down lines, unusually thin walled nozzles, and large diameter manways. Those are the ones that might not pass. 4. Same charts as UG-28. Figure G for factor A, figure CS2, or the appropriate material chart for factor B. For V103 specifically, its manway and any long vent lines get the UG-38 check. Its short feed and product nozzles typically pass without effort. And that's it. Don't spend a lot of time here unless you have unusual nozzle geometry. Before we wrap up, 7 common mistakes on nozzle reinforcement calculation. 1. Skipping the UG-45 minimum. The pure pressure calculation will give you a hair-thin nozzle wall. UG-45 makes you go thicker. Don't skip it. It often governs. 2. Using nominal dimensions instead of corroded. UG-37 uses corroded thickness. Subtract the corrosion allowance from both shell and nozzle before you start. 3. Counting metal outside the UG-40 zone. The zone is fixed by D, R sub n. T, and T sub n. Metal beyond it doesn't count. Don't inflate A1 by pretending the whole shell is available. 4. Ignoring FR1 for different metals. If the nozzle material is weaker than the shell material, which happens sometimes, FR1 drops below 1 and the required area goes up, not down. You need more reinforcement, not less. 5. Double counting overlap metal. UG-42 shared metal between two closed nozzles counts once, not twice. 6. Forgetting the weld area A4. Fillet welds contribute area. Small but real. Include them when the margin is tight. And 7. Not checking heads for openings. UG-37 applies to holes in heads too, but the required thickness in that case is the heads T sub R, not the shells. Different formula, same principle. 6 takeaways from lesson 8. Carry this forward. 1. UG-37 is bookkeeping. Metal removed at the hole must be replaced at the hole. Simple accounting. 2. The available areas come from 4 physical sources. Shell access A1, nozzle walls A2 and A3, welds A4 and pad A5. 3. Only metal within the UG-40 reinforcement zone counts. Load sharing is local. 4. 3 reinforcement strategies: integral, welded pad, self-reinforced forging. All satisfy UG-37. Pick based on cost and service. 5. UG-45 sets a minimum nozzle neck thickness independent of pure pressure. Don't skip it. And 6. Closed nozzles per UG-42 and vacuum service per UG-38. Each add their own rules on top of UG-37. One more thing before we finish. A story that turns the abstract into unforgettable. If everything we just learned about stress concentration around holes is right, then it shouldn't apply only to pressure vessels. It should apply to any structure with holes and cyclic loads. And it does. Here is the most famous example in engineering history. This is a de Havilland comet, 1952, world's first commercial jet airline. Beautiful aircraft. It had roughly square windows, near square, with only a small radius at the corners, which looked elegant and matched the aircraft's clean lines. You already know what's coming. Every time the comet took off, the cabin pressurized. Every time it landed, it depressurized. A pressurization cycle. The stress at the 4 square corners of every window went up to 3 times nominal. Exactly as we said. Cycle after cycle, cracks initiated at those corners. In 1954, two comets broke apart in flight due to fatigue failures at window corners. The entire comet fleet was grounded. The airline industry never designed a passenger jet with square windows again. This is what every airliner window looks like today. Large corner radii, rounded oval shape. Notice how the stress flow lines bend smoothly around the window without crowding. Peak stress at the window edge is about 50% lower than the comet window, well below the fatigue threshold, even after millions of pressurization cycles over a jet's lifetime. Same stress concentration physics as your vessel nozzles. Different industry. Same lesson learned the hard way. When the comet cracked, engineers around the world learned in one weekend what a decade of research would have taught them. Now, every pressurized aircraft, every submarine, every pressure vessel, every ship's porthole, they all have rounded corners for one reason, because loads don't like sharp corners. Now it's your turn to be the engineer. Look at this vessel. It's a real distillation column, similar to what you would see in a refinery or petrochemical plants. Multiple nozzles at different sizes and locations. Some have reinforcement pads, some don't. Here is the exercise. Pause the video right now. Look at each nozzle in the sketch. Which ones do you think need reinforcement pads? Which ones don't? Make your predictions. Then hit play and we will see how you did. Alright, let's walk through them together. The vapor outlet at the top, large diameter on the head. Does it have a pad? Yes, you can see it as a slightly wider band around the base of the nozzle. Big opening, big required area, needs the pad. The feed nozzle on the side, upper part of the column, 6-inch class, similar to what we designed for V102. Pad? Yes, same reason. Large enough that shell access alone isn't enough. The reflux return, opposite side, medium size. Pad? Yes, almost always for anything in the 4-inch and up range on this class of column. The thermowell on the right side, very small, half inch or 3/4 inch, threaded. Pad? No. Under the UG-36 small opening exemption. Reinforcement calculation not even required. The manway, that big oval shaped opening on the left, pad? Obviously, yes. Usually the largest single opening on the vessel, almost always ringed with a thick pad. The pressure tap on the right is smaller than the thermowell. Pad? No, small enough to be exempt. The level connection on the lower left, small to medium. Pad? Judgment call. Depends on the specific size and shell thickness. Might or might not need one. Rule of thumb, large nozzles get pads. Small nozzles like thermowells and pressure taps usually don't. But the UG-37 calculation always has the final word. Now, when you walk through a plant, you will be able to look at a vessel and read the design decisions that went into it. One more idea before we go. This one's bigger than UG-37, bigger than lesson 8. Loads don't disappear. They find another path. UG-37 is just how the code says it. Every engineering discipline knows this. Bridge designers know it. That's why they design load path redundancy into every truss. Building architects know it. That's why they put steel headers over doors and moment frames around openings. Aircraft designers know it. That's why every hatch, every window, every hole in a fuselage gets Doppler plates and rounded corners. Pressure vessels are just one place engineering meets this idea. When you cut material out of a load bearing structure, the load doesn't vanish. It looks for a new path. Your job as the engineer is to give it one by putting metal back where the load has to detour. That's the discipline of lesson 8. That's the discipline of your whole career. Quick look at the road ahead. You are here. Lesson 8. Lesson 1 through 7 are behind us. 8 lessons remaining. In lesson 9, flanges. Every nozzle we design today ends in a flange somewhere. That flange connects the vessel to piping. And flanges have their own code section. Appendix 2 with their own equations, geometry, and design decisions. Bolt loads, gasket sitting stress, flange rotation, hub stresses, and an iterative design procedure that's unlike anything else in section 8. That's lesson 9. All right, Q&A. 6 questions I get from students every time. Let's work through them. Question 1. Do I need reinforcement for every nozzle, no matter how small? No. UG-36 has small opening exemptions. For single openings not exceeding roughly 2 and 3/8 inch NPS in shells 3/8 inch thick or less, or 3.5 inch NPS in thicker shells, the code exempts the reinforcement calculation entirely. Threaded couplings for thermowells and pressure taps usually fall in this exemption. Check UG-36 C3 for the exact limits in your specific case. Question 2. What material do I use for the reinforcement pad? Same strength material as the shell is the default. Typically the same material specification. If you use a lower strength pad material, you must apply FR4, which equals pad allowable stress divided by shell allowable stress to reduce A5. Higher strength pad doesn't help you. FR4 caps at 1. Practically match the shell material and move on. It's simpler and it's what most fabrication shops stock. Question 3. Can I skip a pad by just making the nozzle wall thicker? Yes, that's self reinforced. A2 in the calculation grows with nozzle wall thickness. If you can find your entire required area from just A1 plus A2, no pad needed. This is common for large nozzles where forgings with thick necks are already the standard fabrication. It's cleaner, avoids the pad crevice, and is preferred for cyclic and corrosive service. Costs more upfront though. Question 4. What if my pad diameter exceeds the UG-40 horizontal limit? Extra pad material beyond the UG-40 limit doesn't count as A5. It's not harmful, it's just wasted metal and wasted weld. Design your pad to actual limit. Rule of thumb: pad outside diameter around twice the whole diameter usually stays within limits and gives adequate area. If your pad needs to be much wider than that, you probably need a thicker pad instead. Or you might want to reconsider self reinforced construction. Question 5. Are hillside or angled nozzles the same calculation? Same principle, more complex geometry. The finished opening becomes an ellipse, not a circle. When you cut into a cylindrical shell at an angle, UG-37 uses the long axis of that ellipse for D in the required area term. The reinforcement zone also stretches to accommodate the ellipse shape. Same UG-37 principle, slightly larger required area, and considerably more work by hand. Vessel design software handles all of this automatically, which is why you will almost never do this by hand. Question 6. How do I verify a vendor's nozzle reinforcement calculation? Ask for the UG-37 area summary table. Every commercial code check like PV Elite, Compress, all the major ones produces this table. It lists A required, A1, A2, A3, A4, A5, and totals. Compare available to required. Confirm that the correlated dimensions were used, not the nominal. Spot check the UG-40 limits for reasonableness. If those numbers match your independent hand calculation within a few percent, the design is sound. If not, ask questions. And with that, we have reached the end of lesson 8. In lesson 9, flanges. Every nozzle we design today ends in a flange somewhere. That flange connects the vessel to piping. And every flange is its own little pressure vessel with bolts, gaskets, and a set of forces most engineers find genuinely tricky the first time they see them. Appendix 2 of Section 8 is where it lives. Bolt loads, gasket seating stress, flange rotation, hub stresses, and a design procedure that iterates in a way nothing else in the code does. That's lesson 9. Until then, thanks for watching. If lesson 8 helped you, please hit the subscribe button so you don't miss lesson 9. And remember the bigger idea: loads don't disappear, they find another path. Your job as the engineer is to give them one. See you next time.